The last clip completes the circle and describes how we go from quantum mechanics to getting the R and Y functions that we saw at the beginning of today's lecture. And it is due to the work of Schrödinger. And Schrödinger, shortly after Heisenberg, came up with Schrödinger's equation. Now, the math of Schrödinger's equation is complicated, and so I'm just going to describe its overall features. It's an example of an equation which is called an operator equation. And the famous equation is H. That little hat means it's an operator. An operator means it acts on things. Psi is a wave function. And the operator on the wave function changes the wave function. And for very special waves, they come back to an energy times the same original wave function. So an operator equation is that you're looking for wave functions which have the property that acted on by the operator come back to the energy or some constant times the original wave function. And the very special wave functions that do this have a name, eigenfunction. And eigenfunctions are the solutions to the operator equation. Schrödinger's operator equation for the energy had two terms. There was one term, which I'll call K, which measured the curvature. The curvature is how much a function is curving. And plus a second one, an operator, which measured potential energy. These two operators together are called the Hamiltonian. He knew exactly what the mathematical form of HK and HP are. I give them in the lecture notes, but it doesn't matter. And he realized that the important things were to find the waves, the eigenfunctions, which when operated on by his curvature and potential energy operators, came back as themselves. And I have this I have this example in my lecture notes, which I'm going to go through. And this is daily regime. I should eat 1,600 calories and exercise. My doctor is really nice to me, for 20 minutes a day. And my doc, so there's an operator H1, which is the 1,600 calories. And the second part of the operator is the exercise of the 20 minutes. And if they were to act on the wave, which is going to be called Stephen Lee, if I did that, then the next day I would come back unchanged as Stephen Lee. That's what my doctor says. Let's believe him. So I am an eigenfunction of this operator. But does that mean that everyone that eats 1,600 calories and exercises for 20 minutes? Let's try Dr. Kinsland. Does that mean that Dr. Kinsland, if they have 1,600 calories and 20 minutes of exercise, she's going to be back the same person the next day? You know, she's a parent of 3 children, you know. I don't think so. And so she is not going to come back as Dr. Kinsland. Psi Dr. Kinsland is not an eigenfunction of this operator equation. Psi Stephen Lee is an eigenfunction. And since Schrödinger actually knew the exact mathematical form of the curvature operator and the potential energy operator, he could find the solutions. And when he did that for the atom, he found that the solutions for the atom obeyed always the following result. Psi equals one function, which is the radial function, times one function, which is the y function. And when he calculated them, the solutions, these are the kinds of values he got. He got that 3py. Here, I'll put it up there. 3py is this. 3py is 6 minus r e to the minus r over 3. That's its r function. And its y function is y over r. And let's plot those functions. Let's plot the r function. Well, what's the value of the r function at 0? Well, since it's times r, put it in chat. What's the value of capital R? Since little r is 0, capital R is 0. What's the value at 6? At r equals 6? Well, at r equals 6, 6 minus r is 0. And if you plot the function, you get this graph, which is exactly the 3py r function. And now let's look at y. Well, y is a direction. In the direction going at 12 o'clock, we're just going to look at the points on the circle. At 12 o'clock, it's very positive, because this is the point 0, 1. Y equals 1 here. Here, the value is y equals minus 1. It's negative here. And if I were to plot that, and in this direction, y equals 0. So if I were to plot that, I would get this curve. The negatives I'll draw like this. And the conclusion is that the solution for the Schrödinger equation are exactly the functions which I asked you to memorize at the beginning of, and I talked to you about at the beginning of this lecture. Here they are. These functions here are the solutions of Schrödinger's equation, which means that we could start this lecture all over again. Okay, that's the end for our last clip.